number 10, I believe, is looking for us to find a whole bunch of currents and a whole bunch of voltages. Okay? And it's worded in a way that doesn't make the most sense when you first look at it because of the way you guys have been working problems before. But once you understand what we're looking for and how to break it down, it's very, very similar to everything we've been doing. Okay? It's just a little bit extra. Okay? So we're going to start from our voltage source. Okay? So our voltage source, we can convert from this single cosine to either our rectangular or our polar / phasor form. Okay? So this V source could also be V source with respect to omega would be what, 4.53 times angle 30 degrees. Right? When we do that, we lose our angle information. We lose our omega, right? Omega being 0.333 times 10 to the negative 3. Okay, we lose that information, but it's still useful to us. Okay, now this can also be expressed in the A plus JB form as we just solve it out, right? So it's 4.53 cosine of 30, so that would be 4.53 times root 3 over 2 plus J times 4.53 times 1/2, right? That's 3 different ways to look at the same source, okay? The end result, it's going to ask for answers in this form, so it's pretty easy to convert back, all right? So we have different ways to look at it. When you're working with MATLAB likes this, okay? If you're doing matrix analysis or mesh or nodal, you're going to want to use that kind of form in MATLAB for the most part. Okay, so that's our first step, is getting our stuff in a form we can use. The next step is to convert any inductor values or capacitor values into their reactive values, the reactance, or their impedance values that we're used to dealing with. Okay, so the impedance of an inductor, right? J omega L. So for us, omega is 0.333 e negative 3. So ZL works out to be something like J times 0.999 e negative 6, which is a ridiculous number. And I don't want to write that out that many times. So I'm just going to round, and I'm going to say ZL is equal to J times 1 e negative 6. That's reasonable, I think. Okay, it's not going to change the math that much. So I can actually come back here. I'm just going to go ahead and erase this, because this 3 millihenries no longer has anything to do with the problem. Okay? That 3 millihenries was only there so we could solve for this J 1e negative 6. Only reason it's there. All right? And this Vs here, we're just going to go ahead and call this our 4.53 angle 30 degrees. So, now we're at a point where it's just like every other problem we've worked. Okay? I can find the source current first, right? And the way I do that is I go back to Ohm's law, right? I know that my voltage has to be equal to my current times my total impedance. Yeah? So I need to find my total impedance. When we are working with impedances, it's important to note that impedances behave like resistors. Okay? It doesn't matter if it's a capacitor or inductor that created that impedance, treat it like a resistor. Okay? So, we're going to do this one first. We'll call that Z1. Okay? So 1 over Z1 is 1 over 1 plus 1 over 6, or J times 1 e negative 6. We're going to combine those together, so 1 over Z1 is equal to 1 plus J times 1 e negative 6 all over J times 1 e negative 6. We're going to invert that, so we're going to get Z1 is equal to J times 1 e negative 6 over 1 plus J times 1 e negative 6. Easy enough. So then our next one, our total, the total would just be 10 plus that. 10 plus J1E negative 6 over 1 plus J1E negative 6. Get common denominators, so we get 10 plus J times 1E negative 5 plus J1E negative 6 over 1 plus J1E negative 6. Okay, there's our total impedance. Okay, so our circuit has been reduced to this, right? By combining all that down to one thing. So we can just say, we can go back to Ohm's law, right? Our voltage has to be equal to our current times our impedance value. We know our voltage value. So we go back to our phasor. Our phasor was 4.53 angle 30. Has to be equal to our current times this mess. Okay? I'm going to go ahead and convert this to a phasor just kind of quickly. Okay? If we look at the math, 10 squared is 100 plus 1 millionth, basically, is essentially 10. Right? So this is more or less 10 angle 0, approximately. It's not correct. The angle is like, 2 to the negative 5 or something ridiculous. It's incredibly small, but it is close enough to 0 that I'm comfortable calling it 0. Okay? The bottom one, same thing, 1 angle 0. Okay? So we cross multiply, and I will get our current source is equal to, well, 4.53 angle 30 degrees over 10 angle 0 degrees. Or our current source is 0.453 angle 30 degrees. Okay? There's our current source, which I could convert back to this. This is the same thing as our current source. Our source current is 0.453 times the cosine of 0.333 e negative 3t plus 30 degrees. Okay, that is our source. Now, the next step is finding the drop across the current through each other portion. Okay, so I'm going to erase some of this. And again, if it asks your answer in a single sinusoid or a single sine form, we need to convert back to this. Okay, it's one simple step that should be easy to get to. Okay, now what I found is the current coming in. Right, now this has become a simple current divider, where the current gets divided up a 1 ohm resistor and a 1 ohm something, or a device that is 1e negative 6 times j ohms. Okay, so our current divider, so our IR, voltage going or current going through our resistor, is equal to our current source times our impedance of our other pathway that we don't care about. So j times 1e negative 6 over 1 plus j times 1e negative 6. Okay? I can convert this again to phase notation. So this is 0.453 angle 30 times 1e negative 6 angle 90. Okay, that's important. When you have just j, that is angle 90 over 1 angle 0, because again, that is essentially way too small to be anything meaningful. Okay, so our current through our resistor ends up being, well, we multiply these together, so 0.453 times 10 to the negative 6 angle, we add up 30 plus 90 because they're multiplied, 120 degrees. there is our current through our resistor. The current through the inductor, we do the same idea. We take, instead of doing this in the numerator, we have the 1 ohm in the numerator. Okay? So our current through our inductor ends up being approximately 0.453 angle 30. I'll leave that for you guys to work through yourselves. Okay? And then if I would like to find the voltage across each individual portion, all I do is I apply Ohm's law again. So my voltage across my inductor is just equal to my current through my inductor times 1e negative 6j. And that will give me my voltage across my inductor. Which, if you look at it, coming back here, my voltage across my inductor again, so my current is 0.453 angle 30 multiplied by 1e negative 6 angle 90. I get, let's see, we get 0.453 e negative 6 angle 120 degrees. You get an incredibly small voltage. Okay? Now, if this makes sense or not, we should see that it should. Okay? Because we are operating at an incredibly low frequency. Okay? An incredibly low frequency is comparable to DC. Right? And when we're at a DC voltage, we say that an inductor acts very similar to a wire. Right? And a wire cannot drop voltage. It will drop an incredibly small amount of voltage, microvolts. And it gets all of the current. So what this is actually telling us is that because of our combination, we're getting, and if we look, the voltage drop across the resistor is going to be equivalent to the voltage drop across the inductor because they're parallel, right? So almost all of the voltage in this circuit is dropping across that 10 ohm resistor, right? Because I have 10 ohms connected in series with 1 and an incredibly small number as far as the magnitudes go. Okay, so that's number 10. We'll hold questions for a minute. Let's go look at number 11 over here. Just because solving it practically with numbers, it becomes kind of trivial with the numbers that show up, and I want to show the identity that appears. Okay, so the way I'm going to go about solving this problem is I'm going to solve it by doing KCL. Okay? I'm going to first, again, I'm going to do the exact same thing. I'm going to convert this into a phasor. So this, it has no phase shift, so this is just 25 angle 0 degrees. If I'm putting it into MATLAB, this would be 25 plus j times 0 because, right, cosine of 0 is 0, cosine of 0 is 1, sine of 0 is 0, so the j component drops out. Okay? Next, I'm going to convert this L into a j omega L. Okay? This is why I'm leaving them out, because I want you guys to be able to see this. Okay? Then I have a KCL problem here. If I'm wanting to figure out the current through L, right? My ultimate goal, my current through L would be equal to V2 minus ground over j omega L, right? V equals IR, we just rearrange these things. V equals I times Z, okay? So if I look at this problem, the next thing I do with any KCL problem is I draw my arrows. I draw the arrows of the direction my current is flowing, okay? These can be arbitrary as long as they're consistent. So whatever works for you, make it work, just be consistent. So I'm going to decide that this current is coming in, which should make sense because it's a current source. I'm going to decide that this current is flowing downward, like so. This current is flowing this way. Say this one's flowing this way. And that one is flowing that way. Okay? The next steps are to set up a system of equations. All right? So my first equation, looking at node 1, I'm doing KCL. I want to look at the sum of the currents going in and the sum of the currents going out, and they have to be equal to each other. Okay? So what I have, starting from here, over 1. I get my current coming in is only my 25. That's my only current coming in. So 25, I'm working in rectangle because I'm just going to put it into MATLAB later. That is equal to V1 minus V2 over R2 from here to there. That's the direction the current's flowing because of the way we've defined it, plus V1 minus 0 over R1. Okay? Those are the only two currents that are leaving V1. Okay? We only care about the paths out of town or out of the node. Okay? We're looking at admittance paths. It is an admittance path away from the node. So I'm going to rearrange this equation really quick just to get it into a form that I want to look at it here in a minute. So we're going to say 25 is equal to V1 times the quantity 1 over R1 plus 1 over R2 plus V2 times negative 1 over R2. Okay? And what we're going to see is we're going to see a really repetitive trend where the things we're multiplying V1 by, in this situation, we're concerned about node number 1. The things we're multiplying by node 1 are the admittance paths that touch node 1. So if I just wanted to add in another inductor here, so this was like J omega L2, well, now I have another pathway out. Okay? All this would do is it would add here, it would add another plus 1 over J omega L. You do not have to combine these when you're doing KCL. Right? This is why MATLAB is your friend. So it allows us to simplify things. So I have this form. I'm going to look at node 2. Okay? And I'm going to do the same thing. The sum of things coming in has to be equal to the sum of things coming out. So the only thing coming in is V1 minus V2 over R2. That has to be equal to V2 minus 0 over J omega L plus V2 minus 0 over R3. I'm going to do the same thing. I'm going to rearrange the equations. And this time I'm going to have 0 is equal to V1 times the quantity negative 1 over R2 plus V2 times 1 over J omega L plus 1 over R3. Now what we see again, we see we're in node 2, right? We're looking at node 2. The number we're multiplying by node 2 is just the sum of the admittance pathways out of it. I forgot one. I forgot plus 1 over R2. Now that's right. So it's the sum of the admittance pathways out of it. Now if you look, the number associated with V1 here is completely the same as the number associated with V2 on the first node. Okay? What we do when we are constructing the matrix is the other forms, the things that are shared when we build the matrix, are the negative admittance pathways. Okay? So what you'll see is, so I'm going to put this matrix together. So I'm going to have a matrix of basically I is equal to sum V times an admittance. Admittance is Y. Okay? So I'm just going to erase some space here. So we'll get our I, so 25, 0 is equal to V1, V2 times, well, now we do our admittances. Okay, so 1 over R1 plus 1 over R2, negative 1 over R2, negative 1 over R2, 1 over R2, plus 1 over R3, plus 1 over J omega L. This is now in a state, once you've actually plugged in numbers, where it is now very solvable in MATLAB. What you'll do is you'll say V, once you've defined your variables, V is equal to Y, backwards division, your current. And that will output nodal voltages for you. Those nodal voltages are going to be in the form of A plus J times B. So it will be your job to convert back to a phasor, and then convert that phasor back to a cosine based off of the omega value that we have. Okay? That's how most of the homework problems are in this section. It's something similar to this, if we're dealing with frequency. You can break them all down kind of like this.